Hello. This is the topic about variation of parameters method for higher order ordinary differential equations. Uh, I would like to point out that up to now we have covered this method, variation of parameters method, for second order ordinary differential equations. But it may be worthwhile to consider also the higher order ordinary differential equations. Okay, so for this purpose, let me just uh, just repeat about what was the method for the second order ordinary differential equation. So first of all, we had the equation for the variation of parameters method. We don't have to be much worried that the constants, the coefficients of the equations will be constant. So even in non-constant coefficients, this method works. Okay, so this is y double prime plus px y prime plus qx y, and that is equal to a function r of x. Okay, so r of x. So what was the method? The method was, first of all, we find the solution for the homogeneous case. So for the homogeneous solution, we have the solutions y1 and y2 we already know. Okay, and then using these y1 and y2 solutions, we calculate the Wronskian. Okay, and what was the Wronskian? Wronskian was y1, y2, y1 prime, y2 prime. Okay, and then we apply this formula. So the formula we are applying for finding the particular solution yp. So the formula is minus y1 integral y2 r. Okay, I just simply write r over here instead of r of x. So it's understood that r is a function of x divided by w, and then plus y2 y1 r over w. So this is the formula which is applicable for second order ordinary differential equation. But for example, if we have third order ordinary differential equations, then we cannot apply this formula. We must have some other formula. So we can generalize it. Okay, and then let me show you how can we generalize it. This second order equation, and this formula can be put in two components. So yp1 plus yp2. So yp1 is this one, yp2 is this one. Okay, so in this case, if I see that, then this yp1, I can write it like this. Yp1 is, I can write as like something like this. Yp1, I can write something like this. This is minus y1 times u1. Okay, so y1 is simply here, and then the term in the integral I represent by u1, the term with this integration, and then similarly plus y2 u2. Okay, so this u1, if u1 is this term, y2 r over w dx, so then u1 prime will be simply y2 r over w. Okay, u1 prime will be y2 r over w, and similarly u2 prime will be y1 r over w. Okay, without that integral. Okay, so in this case, this y to r can be written like this. It is can be also written in the form of this determinant. So y to r can be written like this. It will be 0 r and then y2 y2 prime. So if I take the I can verify it like this. Y2, that will be 0, and then that will be minus r y2. Okay, that will be minus r y2. So I can just maybe I can just say that it is the minus y2r. Okay, so in this case I can just remove this part. Okay, so it will be an y1 y1 u1, and then u1 will be this. Okay, and then I will get a function like this, okay, a determinant like this. Yeah, just a small correction. Yeah, we will say because it's a y minus sign is over here, so we can say it as minus, and then we can put minus sign here. So here we can take u1 is equal to minus, so that then when we evaluate it, then that minus sign will be cancelled out. Okay, so it will be plus, and then we can use minus over here. Okay, so y2r we can write it like this. So we can call it as a w1. Okay, and then in this case, for the second case, we can write yeah, u1 was w2r and u1 and yeah, u2. Yeah, so in the second case, this y1r, y1r, we can write like y1r, we can write like this. It is y1 prime, and then 0, and then it is r, so it will be y1r. Yeah, so there is no issue of the sign over here. So you can see that now the solution can be written like this: minus y1 u1 is now Wronskian. Okay, w1 y2r is this. Okay, u2 is then minus this Wronskian. Okay, so minus, and then over w, and then minus minus it will be plus. Okay, and then y2 it will be again, we call it as a w2. Okay, so it will be w2 over w dx. So in this case, now the same equation we can write in the form of the determinants. Okay, right, so in this, the first determinant w1, second determinant is w2, and w1 is simply the same as this w, but the first column has been replaced with 0 and r. Okay, and w2 is the same as w, but the second column has been replaced by 0 and r. So in the same way, if we have we can use this equation for the second order differential equation, but we can also use this type of approach as well for arranging the terms. But I think we are more used to or comfortable of using this formula rather than using these w1 and w2 notations. But however, if we have third order equation, then we will have a 3 by 3 Wronskian. Okay, so w1 will be then 3 by 3, so we will have 3 solutions from the homogeneous part of the solution, y1, y2, y3, and then the Wronskian which we will calculate will be y1 prime, then y1 double prime, then y2 prime, then y2 double prime, y3 prime, and y3 double prime. So this will be a 3 by 3 Wronskian in that case. So in that situation, then we can generalize it because we already know the pattern for 2 by 2. So for W1, we can just simply write in the first column, we will replace it with 0, 0 and R, and then the remaining will be y2, y2 prime, y2 double prime, then y3, y3 prime, and y3 double prime. Okay, and similarly then W2 will be equal to y1 prime, y1 double prime, and then the second column will be replaced by 0, 0 and R, and y3 prime, y3 double prime, and the last Wronskian W3 will be in a similar manner. So it will be y1 prime, y1 double prime, y2 prime, y2 double prime, and 0, 0 R. And then we can apply the same equations, okay, over here. So in this case, the equation we will apply will be, so simply speaking, the particular solution in this case will be then equal to y1 times u1 plus y2 times u2 plus y3 times u3. y1, y2 and y3 are these solutions from the homogeneous part, and u1, u2 and u3 we will determine by for example these equations. Okay, these equations. So for example, let me say that u1 prime will be equal to w1 over w. So from, if we have u1 prime, then we find then you can take the integral of that, then we will find the u1. So from here we can find the u1. Similarly, u2 prime will be equal to w2 over w. And u3 prime will be equal to w3 over w. Okay, so from here we can find u2 by integration. From here I can find u3 by integration. Okay, so in this way the procedure will work. So let's start, let's illustrate it with the help of one example, and this example will continue in the next video clip. So I will take the remaining 1 minute to start this example, and then we will continue it in the next video clip. Okay, so the equation is y triple prime, third order equation, plus y prime is equal to cosine of x. Okay, so the characteristic equation is m cube plus m is equal to 0. Remember that it is y prime, it is not y. If it is y, then it will be 1 over here. It is y prime. Okay, so then therefore it will be m. So this is the characteristic equation, m into m square plus 1 is equal to 0. So the roots are m1 is equal to 0, and m2 and 3 are the complex conjugate roots. Okay, it's very, so therefore we can find the general solution as consisting of the 3 solutions. So y1 will be then equal to 1, y1 will be equal to 1, and